reduction of entanglement due to external measurement. And it turns out that there is a sharp phase transition in the thermodynamic limit, which distinguishes between one phase where the player which is trying to hide the quantum information, where the player who is trying to extract the quantum information using measurement will need an exponentially large system size number of measurements to extract the initial bit string. And that's the phase where, for example, entanglement entropy grows without bound. This is this linear growth of entanglement. And the other phase is where he will only need a polynomial number of measurements. And that's where entanglement, for example, entanglement entropy is bounded and behaves more or less like a classical state. And ever since we published this paper in parallel with other groups, there's been a lot of activity. This is a very partial list that stops in 2021, which means that, I need to make a disclaimer that it's very likely that they won't give credit to someone who deserves it. And also there's a likelihood that everything I'm talking about has already been done. It's very hard to follow. So the structure of my talk is I'm going to give you an intuitive tool to understand a classical, basically an intuitive tool which is completely classical to give you intuition why you should expect such a phase transition, which is known as the minimum cut picture. Then I'm going to use this to explain the existence of this classical population transition and the tension between it and the quantum information transition. And then finally, I'll get to the main part of the talk, which is analyzing the nature of the transition in Clifford circuits. So let me start from this minimum cut picture. What we found a very useful tool, Alexander also mentioned this, in order to investigate entanglement dynamics, are these random unitary circuits. So here you can see time goes upwards, and space goes to the side. And each one of these blue boxes is basically some random unitary gate. And then generally what happens is in the finite system, entanglement will grow until it will reach something of the order of the system size and it will saturate. And a quantity that we can look at to quantify entanglement is what is known as the Renyi entropy. So you can divide your system into two parts, for example, that's the simplest case, and then perform a Schmidt decomposition. That's a very costly, computationally, that's a very costly process. And then you're basically writing your wave function as a sum of the product states and the probabilities and the number of product states you need to describe your wave function faithfully, quantifies entanglement in some sense. And you can use, for example, these Renyi entropies. And here the index is the level of this Renyi entropy. And for example, n going to 1 is the well-known Shannon information entropy. And I'm going to focus on what is known as the Hartley function, S naught, which is basically just the lower of the Schmidt rank. This is an upper bound on the Neumann entropy. And we're going to use this. So basically the idea is that this minimal cut picture is a tool to compute this Hartley function, which does not require to do, for example, this process of Schmidt decomposition, SVD, and so on and so forth. It's a completely geometric question. It works only for these kind of generic random unitary circuits, but it's a very useful tool. The idea is that, if you want the entanglement for a cut, for example, where it appears there's a green line, then try to cut your circuit into two halves, okay? And then you can, if it turns out, this is what we show, that if you minimize over all possible paths, you seek the shortest path, then the number of cuts you get in that shortest path is exactly equal to the Schmidt rank. And again, this is an upper bound on entropy. I also want to point out that this coincides with, there are some field theories that have been developed for these random unitary circuits, which apply in the limit where you take the local Hilbert space dimension to infinity, and then the fluctuations go to 0, and you get classical spin model. And in these classical spin models, the entropy is basically related to the free energy of a domain wall between, say, up and down configurations, for example, and it exactly coincides with this minimum path. Now, the point is that this method does not apply to fine-tuned models, and in particular, the Clifford circuits I'm going to talk about. Okay, so I'm going to skip this due to lack of time, although it's related to something that Said mentioned. And now let me use this minimal cut picture to give you an intuition why you should expect a phase transition. And to that end, what we need to add to the story are the measurements. So Alessandro already explained everything you need to know about measurements. So let's, for example, look at the simplest kind of measurements, which are projective measurements. Okay, and I just intersperse them inside the circuit in random locations. And then you can ask, what does it imply for this minimal cut picture? Remember that the minimum cut is an upper bound on the entanglement. So if the minimum cut goes to 0, the entanglement is definitely going to 0. And it turns out that these measurements, because they reinitiate the spin in a product state, they're basically like decimating a bond in this circuit. What it means is that this minimal cut is going to try and go through as many measured bonds as it can to minimize the cost for the free energy of this domain bond. Okay, and this immediately leads to the prediction of a phase transition, because there is this analogy between a Van-der-Waals grid, which you can imagine trying to drive current through, and our circuit, right? If the measurements are dilute, then the circuit might be a little bit degraded, but overall it's connected. but there's a critical percolation threshold above which the circuit just falls into disconnected patches. And then the minimal cut can basically just go around these circuits and doesn't cost basically almost anything. Okay, so this leads to the prediction of these kind of three regimes. One regime where entanglement will grow linearly in time. So the minimal cut will go through as many islands as it can, but eventually if we make the circuit deeper and deeper, entanglement will grow. Then there is the mirror image of that. Above the percolation threshold, there's just a few lakes here and there, and minimal cut can just go home free, and in that limit, the entanglement is bounded by this correlation length, and in between, it turns out that entanglement grows like a lobe. And to test this, what we did was we simulated frequency simulations using iTensor, using these hard random gates. On the bottom, I don't know how to use this. I see. Okay, so what you see here is basically the entanglement, this zero range entropy as a function of time for different system sizes, and you can see, as I told you before, it rises until it saturates. And now we look at this saturation value as a function of P for different system sizes, and we do finite size scaling. And the finite size scaling is done with, without any fitting parameters. We just know what it should be for percolation, and you can see that it works very nicely, which shows that our minimal cut picture basically works. Okay. Now the next natural step was to look at the von Neumann entropy. Okay, so this is the really interesting and physically relevant quantity, right? The zero range entropy is a completely unphysical quantity. And when we look at this, we see more or less the same behavior. So you can see that if you look at the saturation value as a function of P, at large P, it doesn't depend on system size. At small p, there is suddenly a dispersion of the curves, and it starts to depend linearly on system size. And therefore, there is, naively, there is a transition. But interestingly, the transition doesn't occur at 1/2, like the classical population transition. It occurs at around 1/4. And here you can see the best fitting we could do, PC, and the critical exponent is 2. Okay. This is just small system numerics. There's not much more to say about that. Okay, but the overall picture that is emerging is that there are actually 3 regions. There is one region where the circuit is connected and is capable of transmitting quantum information. There is another one where it is kind of trivially or classically disconnected and obviously cannot transmit quantum information. But there is this intermediate regime where the zero range entropy or the minimal cut fails to predict the entanglement entropy, where the circuit is still connected but cannot transmit quantum information. And it means that the measurement induced phase transition is generally a transition that is occurring on top of a connected circuit. Okay. Now, this is all nice, but let me tell you about a few problems that emerge. Here you can see results from the group of Jed Bixby, from a student ADM Zavallo, and they came up with this brilliant idea to try and minimize the finite size effect and also avoid all sorts of drifts at the quantum critical point. Sorry, not quantum, the critical point. And they use something that maybe people who do look at the numerics of topologically ordered states use to extract this topological term. They looked at some multipartite mutual information, this I3. And the idea is that by carefully adding and subtracting entropies of different regions, you can cancel out boundary terms. And then instead of having this kind of growth at the critical point like the lobe, you have a crossing like a Bender cumulant, and you can see that they predict a completely different value for the critical point. So it's 0.17 more or less, and the critical exponent is closer to percolation. Again, small system numerics, what can we say? But this shows that we really have very little understanding of where the transition is, whether it exists, and what is its nature. So in this situation, what can we do? How can we move forward? So one option is, as I showed you, small system numerics, not very helpful, and especially if you have the background of many-body localization, you know that it's very dangerous to base everything on small system numerics. Another option you heard from Alessandro, people made a lot of progress with free fermion models. So that's definitely a quantum information transition. But again, free fermions are special, right? If time will permit, I need to say a few words about some exact results that we have given for all-to-all circuits, which I think is very interesting. But the main topic I'm going to talk about today, which has been also making a lot of activity, is to use these models where you can do classical simulation of quantum processes very efficiently. And these are, for example, these Clifford circuits and quantum automata. And for example, here below, you can see this table from Adrian Zavalo's paper, where they look at the comparison between classical percolation and these Clifford circuits. For example, looking at the coefficient of the logarithmic growth of entanglement at the critical point, and they claim that it's significantly different from a classical percolation. And that's something I would like to challenge. So this brings me to the main point of this presentation, which is looking at Clifford circuits. So our goal is to understand, these Clifford circuits are extremely simple, and I was always suspicious that they can be, or they're described by a classical field theory or a classical picture, and we want to kind of put this to the test. So what we decided to look at is the following model. So it's kind of a fine-tuned model of Clifford circuits. So general Clifford circuits are, have more moving parts. We took a very unique subset, but I'll explain in a moment why. So we look at C0 gates, swap gates, identity gates, which is basically not doing anything, and measurements. But for the measurements, we're going to use measurements in bed pairs instead of measurements on single qubits. Still a local measurement, but it's a little bit different. And then the parameters that control the model are P, which is basically the density of these measurements on bed pairs and identities. And then the other parameter is R, which controls the ratio between swaps and C0s. Okay, and therefore we kind of want to understand what is the phase diagram, and then see if we can use classical pictures to understand the phase transition. And the first thing I want to point out is that one of the interesting things about this model is that there is no classical percolation transition inside the bulk of this phase diagram. Okay, so it's always connected if you think about it in this minimum count picture. Okay, so just to orient you, these are the kind of configurations you might get. So on the boundaries of p equal to 1, you get fully packed loops without crossings. When you take r equal to 0 but p to be finite, you get a finite density of swaps. So you're going to get fully packed loops with crossings. These are well-known. These have well-known field theories. And then this is some point in the middle of the phase diagram. The idea why we never have a percolation transition. Oh, I see this move. So the idea why this never exhibits a phase transition is because you can convince yourself that even when you have p equal to 1, which is the densest possible situation with measurements, there's always a finite probability that a loop is going to go around. There's kind of these rare large loops that can go around the cut point, and they will always lead to growth of entanglement. In fact, the number of such loops grows logarithmically with system size, so entanglement grows like a log at the boundaries of this phase diagram, and everywhere inside, if we think about the minimum cut, it will grow like a volume. Okay, now we can use this picture to even test this loop picture by understanding that if you add C0 gates to these loops, they tend to disentangle them. So actually, it turns out that these C0 gates act like disentangling. They have a disentangling effect, and they lead immediately to an area. Okay, so to make this more concrete, what my student did is she looked at mutual information. This is similar to what I showed you before. There's tripartite mutual information. Just here it's simpler. It's only 3 regions, but with open boundary conditions. But the idea is the same idea. Basically, at the transition, there is a crossing, and you can see here, for example, 2 crossings. So the phase diagram is like this. We have a volume law. We have a volume law down here and an area law. And as I mentioned before, there is no classical population transition. So this is naively this quantum phase transition. Okay, and now we want to understand the nature of this transition. So to do that, we decided, and this is one of the reasons we chose this model. It's so simple. We decided to use this tool, which is called ZX calculus. So when we draw unitary circuits, we're just using some graphical representation of a quantum process. This ZX calculus is just another way of representing a quantum process using some graphical tool. But the nice thing about it is that these brilliant gentlemen here, they developed it so well that they developed all these kind of simplification rules. So you can just take the diagram and apply all sorts of simplification rules, like, I don't know, like Tetris or something, where rows start to cancel each other, and you can get kind of a cascade, and basically you go from one equivalent circuit to a different equivalent circuit. And we thought this is a very interesting point of view. And in fact, you can see here that there are some simplification rules that actually lead to disconnections in the circuit. So this is very important for us. Basically, for the minimal cut picture, it means that there is an equivalent circuit where it could be disconnected. And here you can see, for example, some point in the phase diagram of the circuit just mapped to this ZX calculus. Yeah, let me just quickly mention that these objects here are called spiders, and they're basically just generic tensors. That's what they are. Okay. And here you can see my student applied these simplification rules. So you can see that low P, we're deep in the volume law phase. The simplification doesn't work. You end up with an equivalent network which is connected but different. But if you're deep in the area law phase, it just disconnects completely. Okay, and then here you can see the probability of being connected as a function of P for different system sizes. And you can see it here. This is basically a classical. It's asking a classical question using an adjacency universe, whether there is a connection between the top and bottom of the circuit as a function of P for different system sizes. And you can see that it shows a clear transition. So it means that there is, again, some sort of classical transition. And here there is an important question, which is whether the transition that we obtain is, which appears above this measurement induced phase transition, whether it's really above it, or whether our simplification tools are basically not working well enough, as it's an open problem, simplifying these circuits. And we are now collecting data suggesting that indeed the transition in Clifford circuits is just a variant of classical population transition, which can only be seen in this equivalent simplified circuit. Yeah, so I obviously am out of time, so let me just do the conclusions. And thank you for listening. Thank you. Very much. Do we have any questions?
Thank you very much. So is there a generalization to element? So this is 1 plus 1. So 2 plus 1, for instance, would you expect that you would use similar relation arguments?
Yes.
In such a situation?
Yeah, definitely. So the idea would be in a higher dimension, you wouldn't have a cut, you would have a membrane. And for the same reasons, a measurement would create a cut in your circuit, and yes, you should have a percolation transition.
We have more questions.
Thank you. Maybe I will take the opportunity of the question to learn a little bit about your multiple model. Can you give us?
Maybe quick. So the idea behind the orthogonal circuit is the same. We want to understand the nature of the transition. What we were really interested in this case was establishing, I showed you in the beginning that there is a tension between like our small system numerics and say the small system numerics in Rutgers or whatever, and we want to show that there is indeed, or to say anything exact about this phase transition. And then we proposed this model where you have basically random unitaries applied between random circuits with probability 1 over R, and with probability R, you measure a random circuit. This is basically your dynamics. And the key ingredient in this model is that if you follow a timeline of certain qubit in your circuit, you'll find that it branches out like a tree, at least initially. After enough branchings, which say are logarithmic in system size, you will start to create loops. But until you do that, you just have a K-lane tree. And then you could imagine that in the thermodynamic limit, the transition on a tree is equivalent to the transition in the orthogonal circuit. And that's the idea. And then, this is too detailed, but the point is that we can use this kind of recursion relation to basically connect one generation of the tree to another, and you can follow the dynamics. And just to give you the bottom line, here there's a very nice analogy to droplets in water. It's the that I can give. But just to give the bottom line is that we find the exact location of the transition for random R unitaries, and it's distinct from this classical population transition. So in this case, we can prove that the two are separated from each other, and we know exactly where the transition is. And I think the most interesting part about it is that the critical properties seem to be BKT-like. So, everyone is doing finite size scaling, for example, these kind of percolation models. It's completely different. So that's, I think, an important lesson.
Okay, thank you very much. I think with this, we are at the end of the session. So let's thank Jonathan and also Alessandro for these 2 wonderful talks again.
I can do like this. So we finished the day. We finished the front part of the day. Now, I want to make 3 little announcements The first thing, actually, given the weather conditions, I propose to all poster holders to migrate your posters outside and glue your posters on the windows from the outside. Then, so that's will be, I guess, funner. Okay. There's even a saturating face transition in closed halls in poster sessions. I can tell you about but now. Second, now something related to the poster session. That refrigerator with variety of beverages is for us. Okay. So go back to it when the